This is a short presentation on calculating sample sizes for epidemiological studies. We will be walking through a few scenarios to demonstrate the process, the challenges, and the importance of calculating sample sizes. Let's start out with an understanding of why we perform these calculations. Sample size calculations are important in designing studies for a few reasons. They make population studies feasible, they help obtain meaningful results, and they keep costs to a minimum. Studying everyone in a large population is not feasible or necessary. Instead, we use sample size calculations to decide how many people are needed to represent the population and the disease or outcome being studied. The other two reasons mentioned, obtaining meaningful results and saving money, go hand in hand. A sample size that is too small can output results that are not very different from each other. If these results only show a slight difference, then researchers cannot be sure the difference is due to the effect being studied, but rather due to chance. A sample size that is too large is wasteful. The extra time and resources you spend investing in an overinflated sample size is meaningless. Sample size calculations help to achieve a delicate balance between cost and data in epidemiological studies. At this point, I'd like to take a moment to familiarize you with some concepts and terms you'll see in this presentation. Most studies can be broken down into a 2x2 table. An exposure of interest is chosen, and an outcome of interest is then investigated. A hypothesis is the idea that a study is based around. Researchers will develop a belief and an opinion on what will happen about a certain topic. The null hypothesis is the idea that no detectable difference exists between the groups in a study. Confidence intervals and power are key values included in almost every sample size calculation. Alpha, or z sub alpha, is the confidence interval, or the level of statistical significance. This is a way to describe the researcher's willingness to determine that the result of a study is significant when in fact it's not. A common value for this alpha is 0.05 or 95%. Such a small margin indicates that the researcher is 95% sure that the results will be generalizable to other populations. Beta, or z sub beta, is the power of a study. This is the willingness to see a false negative, or failing to detect a significant result and therefore failing to reject the null hypothesis. The most common value for power is 0.2, or 80%. This is a more liberal margin because the danger of failing to declare a difference is less harmful than the contrary. Each of the scenarios we are about to discuss will have a different study design. It's important to note because each study design requires a slightly different version of a sample size calculation. Study designs vary when a researcher sits down to answer a question, and there are several options for their investigation. Sometimes, from a completed study, data can be used. In other cases, a researcher needs to recruit participants, possibly because they're investigating a new treatment or a therapy or disease. Study designs also vary in the kind and quality of their results. Study designs will be influenced by the amount the researcher is willing to spend on the study. Each design has its advantages and limitations, and these will be touched on for the different scenarios presented. In the interest of saving time, we will present the first scenario in full detail. The following scenarios will highlight key points but will not be as detailed. We begin by investigating a case control study which evaluates the hypothesis that individuals who have been injured or killed with a gun are more likely to have been shot by an acquaintance rather than a stranger, a terrorist, or a thief. We determine the null hypothesis to be individuals who have been shot by a firearm are no more likely to have a family member or a close friend who own a firearm. To evaluate this case control study, the design includes a group of cases, or individuals killed or injured by an acquaintance with a firearm, and a group of controls, or individuals killed by a stranger with a firearm. Now that our exposure of interest is determined, we can look back and evaluate which of them has experienced the exposure of interest, which is subjects who have a family member or a close friend who own a firearm. A 2x2 table is a common way of visualizing this type of study design. As you can see, there will eventually be 4 groups of individuals. Cell A represents those who were exposed to a family member or a close friend who owned a gun and shot by an acquaintance. Cell B represents those who were exposed and were shot by a stranger. Cell C is the number of individuals who do not have a family member or a close friend who own a firearm but were shot by an acquaintance. And finally, cell D represents those unexposed and were shot by a stranger. Here you see the formula to calculate a sample size for case control studies. It looks quite complicated, but we have it broken down here to make it a little easier to understand. The components here are generally represented in all sample size equations with some wiggle room. We will solve for n, which always represents the sample size. In the next section, it contains the variable r. These represent the ratio of participants that will be in the case group and the control groups. The first box highlighted in the numerator will help us measure the variability that exists in our population. We have already described the levels of alpha and beta as power and level of statistical significance. Finally, in the denominator, we will add the effect size to the calculation. This is the difference in proportions seen in the case and control groups. One way to quickly calculate sample sizes without having to use complicated formulas is to use an online resource. Here we demonstrate the online calculator available in OpenEpi. For this study, it simply requires us to input data for the confidence interval, the power, the ratio of cases to controls, and the percent of subjects from the control group that was exposed to the risk factor. To gather the information needed, we turn to the literature. For effect size calculations, data was obtained through a variety of sources. As you can see here, the reference study found 42% of firearm injury victims lived within a home that a gun was present. The percent of controls exposed used data reported by the Pew Research Center. It estimates that 34% of households in the United States have a gun in the home. The ratio of cases to controls uses the standard rate of 1. This information was entered into our sample size calculator. Sample sizes were calculated for various confidence intervals and power. Here we have the sample sizes we would like to propose the researcher uses for our study. The calculated sample sizes seem very feasible, given that for 2013, the CDC reported over 33,000 firearm deaths. With firearm injuries added to that number, it should not be difficult to obtain up to 2,000 cases. In this next scenario, our group has been challenged to use a cohort study to calculate the sample size for an evaluation of how excessive sodium intake is related to elevated blood pressure, hypertension, and stroke. As an alternative to the 2x2 table, this chart gives you an idea of what the study process will look like in our study. The calculations you will see in this presentation will dictate how many people are needed for this initial population. Next, the population is divided into groups by the amount of sodium intake they have in their diets. Based on our findings from similar studies, we recommend that the study follow participants for 3 years. This will allow enough time for the outcomes of interest to occur at statistically significant levels. Here are the hypotheses. The null hypothesis declares no difference in outcome will exist between the high and low sodium diets, whereas the alternative hypothesis states that high sodium diets will elevate rates of blood pressure, hypertension, and stroke. This claim is unidirectional, meaning the study will use a one-tailed hypothesis approach. This is reflected in the error rate allowance, or our Z alpha value. To define the exposure groups, we will use the cutoff value of 1,500 milligrams of sodium intake per day. The study uses this value because it is clinically relevant, as it is the USDA's recommended daily limit for sodium intake. To decide if a patient has the disease, the study will look at 2 outcomes. First is high blood pressure. A patient with systolic blood pressure reading greater than 140 is classified as having hypertension. Our other outcome of interest is stroke. The measurement for stroke is pretty straightforward. A clinical diagnosis of stroke will qualify as the measurement for this disease. Here we see a sample size equation similar to the one in the previous study, except now we are looking for relative risk and prevalence values. Here is a summary of the literature review and subsequent calculations. Proportions of hypertension were very low in sodium diets, less than 5%, and in high sodium diets, 30 to 35%. We were able to calculate the relative risk from values found in the literature to be 6. Values for stroke incidence are on the right. Low sodium diets have a value of 0.08%, and high sodium diets a prevalence of 0.13%. The relative risk of stroke based on sodium in the diet is 1.23. This slide shows where these values have been replaced the variables in the equation. In the final calculations, we will provide results for a variety of power and type 1 error rates that we have not displayed here. This is similar to the last equation. Here, insert the values we found for prevalence and relative risk of stroke into the equation. We have provided this table to show a variety of options for sample size. Gives both values for outcomes of hypertension and stroke for varying levels of power and type 1 error rate. From the calculations, we have obtained the values in this table for proposed sample sizes. The example illustrates the importance of effect size. The hypertension calculations used a large effect size, and the outcome was smaller sample sizes. The stroke outcome used a smaller effect size, and the sample size calculated for stroke outcome are much larger. This is also due to the fact that strokes are more rare than people with hypertension in the general population. For this study, we recommend using a larger sample size so our results are more likely to be significant for all 3 outcomes: elevated blood pressure, hypertension, and stroke. Scenario 3 will discuss how to get ecological sample sizes. This scenario asks if states in the United States with strong gun control laws experience higher injury rates from handguns or rifles than states with looser gun control laws. First, let's outline the hypothesis, exposure, and outcome of this study. The null hypothesis is that states with looser gun control laws will experience injury rates from firearms equivalent to rates in states with strict gun control laws. The alternative hypothesis is that states with looser gun control laws will experience injury rates from firearms that is not equivalent to rates of states with strict gun control laws. So from this, we can say that we will look at the exposure of states with strict gun control laws and the outcome as injuries from firearms, which includes death. The question here is, why are we conducting an ecological study? In this scenario, it would be time-consuming and costly to obtain individual data. The main purpose for this study is to generate a hypothesis, which is to say this study is performed with the intention to conduct further research or prove a need for more in-depth studies. So an ecological approach is appropriate here as it will provide a broader reach for lesser cost than an individually based study. To define our parameters, we will first look at exposure. Open carry and concealed carry laws will be used to classify the exposure. These laws determine how citizens can carry firearms in public, reflecting whether laws for gun control are strict. Our non-exposed group will be loose gun control. These are states where no permit is required or the law is unrestricted for open carry of firearms. The exposed group will be defined as strict gun control, or states that do not permit the open carry of a firearm. Since our outcome is defined as injuries from firearms, injury rates from firearms in each group can be used as our convenient measure for the outcome in the comparison. Here's the formula in this ecological study. If we look into it with patients, we find that it's not much different from the ones we've seen before. We need the ratio of cases to controls, which is now denoted by K, a confidence level of alpha and power beta, which we're familiar with, the proportions of outcome in the 2 groups, and the ratio of unexposed to exposed in the sample. We obtained the proportions of injuries of the 2 groups and the status of policy laws regarding gun control by state from the websites of the CDC, the U.S. Census Bureau, and the Guardian. With data integration, we get the injury rate from firearms and classify all 51 states into two groups. The injury rate from firearms of the exposure group is 9.31 per 100,000 population, and for the non-exposed group, 13.08 per 100,000 population. We utilize parameters of alpha equal to 0.05 and beta equal to 80, and K, the ratio of exposed to unexposed, equal to 1 to get our sample size. The sample size calculated from the previous equation is shown here. 1.2 million participants will be required for each group, totaling roughly 2.5 million. The study must take care to be aware of and avoid ecological fallacy due to time trend, that is, the crime rate change over time. Additionally, future studies are needed to find the direct association between gun control laws and injury from guns. Also, we should pay attention to the potential effect modifiers and confounders such as region of country, Republican or Democratic governors, and population density. That wraps up our final scenario. As a recap, to perform a study size calculation, you must first identify the research question and the study design. Then, you will determine the effect size that you want to investigate. Following, you must research the variables to get values to insert into the equation. Finally, you can select your sample size based on your desired levels of alpha and beta, which are power and statistical significance. Thank you for your time and attention. We hope this presentation improved your understanding of the importance of sample size calculations. Hopefully, next time you're asked to perform a sample size calculation, you can do so with less intimidation.